I think yesterday we have completed the potential and capacitance. Sure. Yeah. We plan to start the new chapter, current electricity. Okay. Unfortunately, it came in online. Okay, no problem. Coming to here, the chapter current electricity. Okay. Till now, what we have discussed, Nana, taking the conductor or insulator, conducting or non-conducting. Body is taken, some charge we are providing. Keep in mind, means by removing the electrons, by adding the electrons, we are providing some charge to the conductor. Okay, that charge, if you give it to the conducting body, that spreads all over the dimensions like length, area, and volume. Okay, if it is a non-conducting sphere, whatever the charge you are giving, where you give, there only it stays. Okay, this was the concept previously what I have discussed. Suppose this is non-conducting ring and I give the charge here, then the charge resides there only in case of non-conducting ring. If it is a conducting ring, whatever the charge you have given there, that spreads all over the surface. That is the difference between conducting and non-conducting. Okay, yes, but here today in the class we are taking a conductor, not the non-conductor, but we are not providing any charge to the conductor. Means this is a conducting wire like copper wire, some wire. Okay, having circular cross sections here. These are the cross sections at the two ends. Okay, so what we are doing, I'm not providing any charge, not removing any electron, not adding any electron. Okay, so here specifically if we speak, it is a neutral conductor, but it is a conductor, not non-conductor. Okay, so here inside the conductor, if you see the known concept, what all of you know, there are surplus of free electrons. These are free electrons, like the gas molecules in the gases. Okay, they randomly roam here and there, continuously like this. Here and there, randomly they move. Okay, due to the random motion, what happens? Net flow, if you see at a point, due to the random motion like this. Okay, zigzag. This is actually in first year kinetic theory. We call it as Brownian motion. I think you know the name Brownian. Remember the name, Nana? Brownian motion? No. Yes. Good. So due to this random motion, what happens? The free electrons inside the conductor, right? They are in motion, not at rest, moving randomly. But if you select a particular cross section in the middle, some cross section in the middle, all together, due to the random motion, we won't find any flow of electrons. Means suppose in a time t, 5 electrons crossed. Okay, this is a random motion. Again, 5 electrons cross inwards, outwards, inwards. So net flow equals to 0. Okay, so the same point I am going to write here. What? Due to the random motion, what I say, the net flow of electrons through a particular cross section is 0. Okay, like 5 students went out to washroom, again 5 students entered into the classroom. Means finally what happened? Neither loss nor gain of the number of students in the classroom. Net flow we say 0. In the same way here electrons cross towards right, cross towards left. So net flow equals to 0. So the main disadvantage you observe here, even though it is a neutral conductor, since it is a conductor, we are having, means the conductor has number of free electrons. Okay, inside the conductor. Inside the conductor, there are number of free electrons. But the only disadvantage is due to the random motion, we are not getting any net flow. That's why specifically to flow in one particular direction, what we are doing now, maintain some potential difference. Why? Because in charges and fields we discussed, the charges are accelerated when you maintain a potential difference between 2 points. Okay, that's why maintain a potential difference. Like this is suppose negative and this is positive, some potential difference. Difference in potential between these 2 points, let it be V. Okay, this is what I am taking V. Potential difference. V is PD. Due to the potential difference, what happens? There might not be any random motion. Why? Because electrons are repelled by the negative, attracted by the positive. So the electrons start moving towards right from lower potential to higher potential. Keep in mind, this is low and negative positive is high. They are trying to move from low potential to high potential. Okay. When electrons start going, means after ringing the final bell, all the students hold their bags and they try to leave the classroom. Means no one is ready to enter again into the classroom. Okay, at 5:20 in the college. Okay, means all the students are moving in a specific direction. That time we can find some net flow through the conductor. Okay, that net flow of charge per unit time is named as, we are going to start this chapter now, the electric current. Okay, so what is electric current? Is I is nothing but the net flow, okay, through a particular cross section in a conductor per unit time. This per unit time we call it as rate of. So rate of flow of what? Charge through a cross section is defined as electric current. Okay, so this is the basic definition, Nana. From the basic definition, what next we try to say here, the unit, no need to mention, all can understand. Coulomb is the unit of charge, second is the unit of time. But this was found by the scientist Ampere. That's why it is taken as 1 ampere. Okay, represented with the letter capital E. Keep in mind, this is all of you remembered fundamental physical quantity. Nana. Electric current is fundamental physical quantity. So 1 ampere. So 1 ampere of current is equals to 1 coulomb per second we see. Okay. And in first year we have discussed while saying about the scalars and vectors. Additionally, we have discussed tensors. Remember, Nana? Yes, exactly. We have discussed tensor. Now we are getting one more tensor here now, here in this chapter. Who is the tensor? Electric current. I think you remember this point. It has the direction, but not obey the law of vectors. Addition of vectors. A bar plus B bar equals to like parallelogram law of vectors. We won't apply. Right in first year only, I think I said. When two currents, yes, two currents are flowing through wires, two wires like this. Net current, we say I1 plus I2. We won't say if the angle is theta root over I1 square plus I2 square plus 2 I1 I2 cos theta. Okay, I think all of you remembered. You are responding there. That's a good sign. Yes, exactly. So it does not obey the parallelogram law of vectors, vector additions. Okay, we add just like scalars, even though there is some angle between the flow of directions of current. Okay, that's why it has the direction, does not obey the vector laws. That's why it is a tensor. Okay, it has a direction, but not obey the vector laws. Okay, they are added like scalars, behaves like a scalar. Yes, exactly. Here. Okay, this is the basic part, Nana, about the current. So what we have to remember for the flow of current, we have to take the conductor, not the insulator. First thing you have to remember. Number two, for the flow of current, no need to give the charge to a conductor. It is a neutral body. Number three, already there are surplus of free electrons inside. Okay. Just by maintaining the potential difference, we are sending them in a specific direction. Okay. To flow in a specific direction, we are maintaining the potential difference. So potential difference is required if you want to see the flow of current through a conductor. If you want to see I, you need the potential difference. Okay? Means without V, there is no I. Okay? Right. Like without Sharad sir, there is no Sharad Junior College. Like without V, there is no I. Okay, potential difference is required to produce the current. Yes, thank you, Srinidhi Priya. Okay, here, this is V. So, if V is more potential difference is applied. Okay, by that what happened? More acceleration you will get for the electrons, Nana. How you get the acceleration, sir? Okay, the potential difference across 2 points usually develops what, Nana? Electric field. Am I right? Okay. So electric field is always from positive to negative, Nana, not negative to positive. Yes, this is the direction of electric field due to the potential difference. Okay. Positive to negative, exactly. But look at the charge is moving in opposite direction. I think recently we have discussed this point in the class. Negatively charged particles are accelerated in opposite direction to whom? The direction of electric field. Yes, in the opposite direction to E, the negatively charged particles. Since electrons are negatively charged particles, obviously they accelerate in opposite direction to the electric field. They are accelerated, not decelerated, keep in mind. So due to that acceleration, what happens in a specific time, more number of electrons will cross the junction. Will cross the cross section. More electrons cross, you will get more current. Am I right? Okay. So with the increase of V, according to the formula, E is equal to minus dou V by dou X. That is V upon potential difference, V upon, if the length of conductor is L, you can take V upon L. Okay. If V is increased across the length, E will be increased. If E is increased, then more electrons cross the junction in a given time. So more current will be there. So ultimately look at here, if V is increased, current will be increased. Means what I am trying to say, whether they are proportional directly or inversely. For that I explained this concept. They are directly proportional. Exactly, directly proportional. Okay. By saying V directly proportional to I is called as Ohm's law, Nana. Okay. So V is directly proportional to I. This is Ohm's law. Ohm found first time this relation between V and I, between Sharath and Sharath College. Okay. This is Ohm's law. So here, according to Ohm's law, what we write next? We have to remove the proportionality, write a constant. Okay. V is equals to I times that constant also all of you know, learnt in 10th class I think. Okay. R is called as what, Nana? Resistance. All of you know it. Okay. Resistance of whom? Resistance of conductor. Why? Because we are taking the conductors here for the flow of current. Okay. Right. This is Ohm's law. Resistance, yesterday only I think we have discussed in the class. It is the opposition, like speed breakers on the road. Okay. It is the opposition for the flow of current from the atoms present inside the conductor. Okay. That resistance, new physical quantity you found there, Nana. Okay, if you find the new physical quantity, immediately we have to give the units. You know, of course, unit of it, ohm, is ohm symbol. Okay, right. This is the first page, Nana. Any doubts in the first page? Very basic fundamentals. I think you don't have any doubts. Very, very basic. Yeah, good. Very, 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 very basic concept. Okay, that too you know in 10th class, all these things. Right? Good, good, good. Good morning, Gomadicha. Anaya. Yeah, here. Next, coming to, shall I move to next page, Nana? Yes, yes. Moving to next page. So, in the first page, observe, we have found two formulae. One is Ohm's law, another is I equals to Q by T. So how to use these formulae when we come to numericals, coming to applications of the formulae. Okay. Practically you observe here, what is this? Right. But practically you observe there, here, if you give more time, more charge will cross. So Q is variable, T is variable now. Okay. So shall I write I is equals to, in variable form, dq by dt, differential form. Okay. Right. This is one model. And in reverse also we can write in integration form, number 2. Yeah, good. Q is equals to integral by taking the cross multiplication I dt. Okay. You are integrating with respect to time, so limits will be from t1 to t2. Second model. And here third model, if I take a graph between q and t, look at I is the slope. If I take a graph between I and t, it is multiplication. Multiplication means area. Ah, yes, good. So integration in graphs used to find the area. Differentiation is used in graphs to find out the slope. That already you know in math in first year. That's why third model, graphical model, if I take here q and t graph, sorry, this is q and t. Q on y-axis, t on x-axis, dy by dx, exactly, dy by dx, perfect. So if I take a straight line or a curve like this, anything, whatever, okay, there is no guarantee that charge changes with the time linearly, okay. There might be a chance even like this, a curve, suppose if I take, okay. Then we can say at an instant, what is the current? Means slope. So at that time t1, if you find the slope here, this is slope. That slope gives the current at t1, current in the conductor at t1, okay, at the time t1. And here fourth point is what we have discussed, the area integration. So suppose given one graph like this. This time I'm taking I on y-axis, t on x-axis. So I into dt, area. So suppose the current changes here like this with the time. Okay. Then we can say this is the shaded area under the graph. That area gives the charge flown through the conductor, charge flow in a time t. For how much amount of charge flows in this time t, up to this time, from t equals to 0 to t equals to me, like from t1 to t2. Okay, good. So these are four models related to it, Nana. Again, they are basic models. Okay. Related to basic models, if I give the numericals, I think you can solve them quickly without my help. Okay. Are you there on bed or in chair with the book and paper? In chair or bed? On bed. And table, neither chair, not. Okay. You are on the table, Charanjit. In chair. Okay, right. Chair with a book and pen. Yeah, super nana. Siri. On ground. Srikar, you are topra. Okay, good. Coming to here. Why? Because I am going to give a numerical to solve. Okay, you have to solve it. Are you ready? Yes. Okay, then start the first one here. Yeah, coming to here. First question is in a conductor. Look at that. I'm giving Q changes with the time as Q equals to 2 plus 3t plus 4t square minus t cube. Okay. Find current in, this is non-uniform manner, in t is equals to say some 2 seconds. Is it 7? Wow. Srinidhi Priya very quickly responded. All of you agree, Nana? She is saying it is 7. Still, these people are doing. 2 plus 6 plus, is it 8? Charanjit is saying it is 8. No, Charanjit, many are saying it is 7. Once you check, I is dq by dt by differentiating. Sai Srikar also, new person also saying it is 7. dq by dt, that is 3 plus 8t minus 3t square. Okay, good. By substituting 2, 16 plus 3, 19, 19 minus 2 2s are 4, 4 3s are 12. So it is 7 only. 7 is correct. Okay. If it is in coulombs, then the answer is amperes. 7 amperes. Okay. Very good. Easily all of you solved. Okay. And here sometimes look at it is varying with the time how constant t power 1, t power 2, t power 3. That's why we need some differentiation. Okay. Sometimes without differentiating, you can say like y equals to mx. Directly you can say m is the slope. Okay. Means in a conductor, if I say q is equals to like a 3t plus 4 or 3t minus 4 or equals to 3t, means mx plus c, mx minus c or mx. I think no need to solve this question. Directly you can say slope is 3. Slope is current. Directly you can say. Okay. Yes, I equals to 3. These are easy questions. Right? So I equals to how much? If they ask, no need to go to differentiation even. Directly you can say, sorry, no, slope is equals to 3, sir. Slope is 3 means slope is current. That implies I equals to 3. If they are in coulombs, I equals to 3 amps. Okay, better I write in coulombs. Then I equals to. These are easy, very easy models. Okay, am I right? Is there any toughness in the question, Nana? Not at all. Like LKG questions. Yeah, exactly. LKG questions. Okay. Even the second model also, if I ask, you can solve. Okay, again, ready with your pen and paper. And without my help, you try to solve. This time I'm saying in a conductor. Okay. I is equals to first model I am saying like 3 amps. Number 2, I is equals to 3t plus 4. Okay. In both the cases, find the charge flows in a conductor. Already I said in a conductor, charge flows in a time t is equals to 1 second to t equals to 3 seconds. Okay, I think you can say the answer for it. Shashank this time quickly responded. 6 for the first one. For the first one or second one, Shashank? 3 twos are 6. First, yeah, exactly. 3 twos are 6, correct. 3t square by 2 plus 40. Second one, I think you have to do. All of you started doing? 20, second one. Oh, Srinidhi Priya saying it is 20. 20 only? Okay, very good. So first one, integral 3 amps through 3 dt, that is simply 3t. Yeah, in the limits 1 to 3. This is equals to 6. Exactly, Nana. So I think all of you completed. Sai Srikar also completed. Q equals to integral. This is 3t plus 4. So after integrating, I am not doing. I think all of you completed there. So I am believing. Shall I believe you all, Nana? It is 20. Okay, right. From 1 to 3. I am not checking. Directly putting the answer here 20. This is 20 coulombs. That is 6 coulombs. Okay. This is also easy for you. Right. And now I am seeing here 3. Oh, sorry. Just here a small mistake. 3t square by 2. Exactly. Exactly. 3t square by 2 plus 40. Right. Now in a graph I am seeing the charge flows through a conductor. I mentioned like this. This is I third example. Example 3. This one also without my help you can solve. I think this is second one. And this is first one. Okay. So third numerical we are trying now. Is it third one, Nana? Oh, sorry, what happened? This is not the second one, I think. This is the second one. Yeah, exactly. Okay, right. Coming back to the I and T. Here I am saying this time very simple graph given like this. And here the current value is 10 amps and this is 6 seconds. What is the charge flown through a conductor? Q equals to how much? I think you can solve it very quickly. Area. Is it 30 nano? Yeah, exactly, I think. Half base into height. Yes, yes, 30. Exactly, exactly. Accepted. So answer here Q is equals to area under the graph. Okay. That is that is equals to directly we say area under the graph half base into height. That is equals to 30 coulombs. This is also very easy question. Okay. And related to the other graph, again one small question, you can solve it again. That is Q and T graph. You can easily solve this one. Here I am giving this time Q and T. Okay, the angles are here, this is say 45 degrees and this is say 15 degrees. This is the charge flown through a conductor, how it varies with time in the conductor A. This is in the conductor B. What is the current flowing through the conductor A to B ratio equals to how much? I think you can say it. This time I think you have to find out I is equals to slope. Why? Because it is QT graph. So slope of A by slope of B we have to take. Why? Yeah, 1 by root 3. Yeah, exactly, 1 by root 3. Srinidhi Priya is correct, I think. Slope tan theta. So first one makes an angle 45 degrees. So tan 45 divided by second one is not 15 degrees now. 45 plus 15, second one is taking 60 degrees there. So tan 60. Harsha is not there. Harsha joined today. Yes, Harsha responded now. Yep, okay, good. So here the ratio is equals to, yeah, 1 by root 3. Size 3. Yeah, exactly. 1 by root. Okay. Yeah, till now all the questions you have solved. It is just a quick walk. Simply you solve all. Right? Now the question is here we are going a bit deep into the concept. This is a charged ring. Okay. It is not a neutral conductor. Charged ring. Some positive charge is given to it. But it is a conductor. So uniformly distributes over the surface. Okay. There will not be non-uniform distribution. Why? Because it is a conductor. Okay. So in this case, if the radius is given as, here r is equals to say some 10 centimeters, and the ring is rotated about the center, means it is the axis of rotation, with some angular velocity. How much is r? That is equals to 10 radian per second. So look at there, what the information given. Omega is given 10 radian per second and radius is given as 10 centimeters, means 0.1 meter. This is the information given to you. Okay. And the total charge given to the conductor Q is equals to 10 like some millicoulomb. Find the current developed due to the rotation. Okay, I developed on the perimeter. Equals to how much? Okay, then we need a concept here, right? Look at, it is rotated with a 10 radian per second constant. He is trying to rotate with some constant angular velocity now. Okay, if it is rotated with a constant angular velocity, observe there, by selecting one small element in this conductor of charge, say some dq, okay, for the length dl, constant angular velocity means to complete one rotation here, it takes a time we know, that is 2 pi by omega, since omega is constant. Okay. So here, yeah, that is the advantage. So here what we say, I is equals to, he is asking, so directly you come to here like, oh, sir, here I is dq by dt, sir. Okay. The element I am taking dq only, sir, divided by dt. Okay. But dq is nothing but like lambda into dl, sir. No need to explain, I think. divided by dt, sir. Okay. The dl is rotating with the constant angular velocity, sir. Okay. So lambda is equals to dl. We write r d theta, sir, divided by dt. Are you able to follow none of my steps? Are you able to follow? Dq for how much length? The length is dl here. Okay. dl, I think you can understand. Oh, sorry. What I here you can understand. dl is r t theta. You know that point, Nana? Yes. That is equals to r d theta. I think all of you know it. Many times we solved in first year and second year. This is d theta, sector principle, Nana. Okay. Right. dl is equals to r d theta. So dq is lambda dl. No need to explain. So r d theta by dt. d theta by dt is nothing but omega. Okay. So we got a new formula here, lambda or omega, when some charge rotates on the circumference of a circle. Okay, you can remember it as a formula. Okay, so using the formula, you can see that implies what? I is equals to lambda, uniform distribution kada. So q by 2 pi r times r omega. So R, it is independent now completely. So you are getting what? Q by 2 pi times omega. That's it. So here radius is unnecessary data. Q is given to you 10 millicoulomb. Omega also given 10 radian per second. So directly substitute there. Q is 10 millicoulomb into 10 radian per second divided by 2 pi. That is how much now you are getting? 50 upon pi millicoulomb. So current will be milliampere. Is it right? Any doubt here, Nana? No. Yeah, good. This is little bit application. I equals to dq by dt, bit changed like this. Okay? Right. Good. If omega is variable, Nana, in the same formula, we can't change anything. Why? Because here d theta by dt he gave. That is nothing but omega. So here if omega is varying with the time, means acceleration, angular acceleration. If omega changes with the time, same problem. So don't go to any differentiation or integration. That's why I'm saying this problem. Okay. If the above ring is rotated with omega is equals to how much he gave there now in the previous problem, 10 radian per second kada, like 10t, or omega is equals to 10t plus 4. Okay, like something, or 10t square. Okay, better we do like 3 models. 10t number 1, number 2 10t plus 4, and number 3 10t square. Like this, if we rotate, then I develop equals to how much, if they ask. Okay, how we solve now if they ask? Same way, there will be no differentiation and integration. That's what I'm saying. Why? Because already by replacing d theta by dt, we got omega. If theta is given, how the theta changes, then we can differentiate. Otherwise, we can't do anything here. Are you following my point, Nana? And what I am saying, I is equals to, you got lambda r omega. Okay, that is nothing but q by 2 pi into omega. Directly by substituting the omega value here, whether it is constant or variable like this, we will get I. Now you follow? Direct by substituting, we can't do anything. Yes, by direct by substituting. And in first case, what I am saying, I is equals to q by 2 pi into 10t. That's all, over. Okay, we substitute q value, we substitute t value. After how much time the current developed, if they ask, we can solve it. Number 2, I is equals to q by 2 pi into 10t plus 4. Further, we can't do anything. Substitute q value, substitute t value. No differentiation, no integration. And number 3, observe there, I equals to q upon 2 pi times 10t square. That's all. Substitute t value, substitute q value. Directly you will get the answer. So don't get confused. If omega is given as variable with the time, okay, whether we have to do integration or differentiation. All the times we won't integrate and differentiate. According to the formula only, we integrate and differentiate. Did you follow, Nana, what I said? Good, 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 good. This is the model. Okay. So do you have any doubt here in this fourth page and third page? No doubt. Even in third page also. Right. Good, good, good. This kind of model he asked in exam, Nana. What he asked in the Bohr's model of atom. Okay, Bohr's model I think is applicable for hydrogen and hydrogen-like atoms. Okay. In the Bohr's model of atom, who are revolving around the nucleus, Nana? Electrons kada? Electrons. Yes, exactly. If the electron is a negatively charged particle, Nana, in an orbit only one electron will revolve. Okay, we accept. According to Bohr's theory. Why? Because there is only, it is applicable for single electron atoms. Okay, you know the restrictions and limitations of Bohr's theory. So only one electron revolves in the orbit. So only one electron in the first orbit or second orbit or third orbit, that is a negatively charged particle, it is revolving and like the charge is rotating in case of ring. Same model. Here positive charge 10 millicoulomb rotates. There 1.6 into 10 to the power of minus 19 coulomb rotates. Okay. And the advantage in Bohr's model is no need to take any variable omega. Why? Because for the revolving electrons, that too in Bohr's theory, they revolve in circular orbits. Circular orbits, omega is constant. They revolve with constant angular velocity. Okay, I think you know it. So in Bohr's model of atom of hydrogen, I am taking, find the current developed in in simple Bohr orbit. Who is the Bohr orbit, Nana? First orbit actually the Bohr orbit. Keep in mind. Okay, yes. First orbit is the Bohr's orbit. Okay, so in first orbit the electron is revolving, so how much current will be developed? So again, I am not deriving all the things directly. I go to here, whatever I derived in the previous page. I equals to q omega upon 2 pi. Okay, directly coming to here, q omega upon 2 pi. If I know omega, I substitute. If I don't know omega, again I go with. In case of electrons, omega is constant. Then happily I can write omega equals to V over R. From V equals to R omega in circular orbit. So I am going to write here what, replacing the term omega with V over R. But I don't know how many remember the velocity formula and radius formula given in chemistry. R equals to Bohr's orbit radius. Anyone remember, Nano? Actually 0.529 angstroms. That 29 rounded off, so I am taking 0.53 angstrom. Okay, keep in mind, this is the first orbit radius in hydrogen atom. Okay, do you know this or not in chemistry? No one is responding. We know it, but not remembered. Okay. Okay, good. 0.53 angstrom. And speed of electron in first Bohr orbit. Anyone remember? Okay, 2.18 into 10 power 6 meters per second. 2.18 rounded off, so 2.2 approximately we take. Okay, and Q, only one electron, this is hydrogen atom, only one electron revolve in an orbit. So Q equals to 1 E, that is equals to 1.6 times to 10 power minus 19 coulomb. I think now you can solve it, Nana. You are at home, even by using the calculator also you can say the answer. Am I right? Radius is 0.53 angstrom. Angstrom, remember the value, Nana? 10 power minus 10 meters. Okay? With your weapons. Finally, how much you got there? I equals to what your cal C is saying. Are you using C? Cal C calculator? Anyone? Do it quickly. 2 pi is 6.28. V is 2.2 times 10 power 6 upon R is 0.53 times 10 power minus 10. Oi, Shashank, will you get 10 power minus 23 there? I think 1 point approximately 0.6. Okay, 0.57 or 0.6 approximately. Yeah, 10 power minus 3. Is it correct, Nana? 1.057. Okay, okay, yes, yes. 1.057 rounded, nearly 1.06 times 10 power minus 3 amps. Okay, very good. So for this problem, what we have used, same q omega by 2 pi. This is previous question now. Okay, given in exam, but a little bit changed. We wrote it as like qv by 2 pi r. by taking omega is equals to V by R. Replace that term. Okay. So like you can change its form, Nana, that's it. Okay. Finally concluding here, I, you can write it as q by t, that is your wish. dq by dt in case of variation. Okay. In case of revolving electron or something, we can write it as q omega by 2 pi. Again, by taking omega to the denominator, you will get q upon 2 pi by omega. 2 pi by omega is what, Nana? Time period. Yes, time period. Q by t you can write. And reciprocal of time period is frequency. As q times 1 by t is frequency. Nu here is frequency now. T here is time period. Okay. All right. Good. And even you can write the currents developed in different orbits means we can see in all orbits hydrogen like atom only one electron revolve. That electron is suppose in first orbit or second orbit or third orbit like. Okay. We can say I is inversely proportional to time period. Okay. And for circular orbits, according to Kepler's law, applicable for microscopic and macroscopic, even for electrons also we can apply. T square is directly proportional to R cube, R power 3 by 2. Yes. And the radius in your chemistry, radius of orbit is 0.53, I think remembered, angstrom into n square by z. Remember this formula, Nana? Yes. That implies T is directly proportional to R cube, R power 3 by 2 means n cube upon z power 3 by 2. Is it right? 0.53 is constant. Any mistake here, Nana? That implies you can write from chemistry I is directly proportional to 1 upon T means z power 3 by 2 upon n cube. So if you go to depth into the concept, you will get different types of equations like this. Okay, this is actually derived from here. Okay, this is used actually here. That is actually used here. This is actually taken from here. Okay, this is the link between physics and chemistry. So are you able to solve these kind of models, Nana? Currents developed, suppose they ask the ratio in a hydrogen like atom or in a hydrogen atom. Hydrogen atom means Z is constant. Directly you can take I is proportional to n power minus 3. Same Z. Okay. I is proportional to n power minus 3. Taken to the numerator. In an atom. Hydrogen like atom. Okay. So if they want to compare the ratio of currents for like a second orbit, third orbit, like, okay, you can use this concept. Able to follow none of these things in this page? Why? Because this page, in this page we went to application. Okay, not basic models. Applications we went to. But do you have any doubts? What size recon new person? No. No doubt. Okay. No doubt. Very good. Very good. Then we are moving to next page. Okay, shall I move to next one, Nana? Yes, yes. Okay. This time, still we are going deep into the concept, like advanced type of questions. Okay. From basic model, we have started, Nana. From basics, just look at there. On one formula, we have done all these things. I equals to dq by dt or q equals to integral I dt. Not yet entered into v equals to IR. Okay, in the first page, what we have discussed. Just the first half of the part we are discussing. Okay, I equals to q by t from this basic formula. From this basic formula, we are doing the applications. Right? Not yet entered into the second formula. Look at there on the first formula only how many applications are there. Okay, these are the applications. And now still not yet completed. Suppose entered into the advanced model. What's that? Instead of the ring given some amount of charge, I'm taking, I think you remember, you understood what I'm going to take, a disc or sphere, like such type of elements. Suppose if I take the disc of radius something I'm taking here, whose radius is r. This is a conducting disc. Conducting means uniformly distributed, the charge. Okay, some amount of charge is given to each. That spreads all over the surface. Means we are going to take the sigma concept here. Okay, this is the spreading of charge on the conductor. I am taking some positive amount of charge. Q is given all together. Right? This is Q I am taking here. Now in the same way what I am doing, trying to rotate this disc with some angular velocity about its center. Okay, this is the center, about its center. I am going to rotate. Okay, just like how we rotated the ring here now. Here we rotate the ring. In case of ring, without finding out, even though we found some small hiccups, but finally, without getting lot of hiccups, we got I is equals to q omega by 2 pi, finally, right? But here, what the disadvantage you find there? It is actually part and parcel of many rings, not one ring. Disk is part and parcel of many rings. Am I right? So if you assume a ring here, then for the ring you can use the formula q omega by 2 pi, not for the whole disk. I think you got my point. Am I right, Nana? If you assume a ring here of some thickness like this, some thickness I am taking. This is the thickness here. 1 minute, please. Okay, sorry for the distance. And here, for this ring, if you are able to find out the charge present on the perimeter, then I think it will be easier for you when it is rotating with the constant angular velocity omega. Okay, so if it is rotated with some angular velocity, actually what we have to say, Nana, for the ring, find the equivalent current developed. Okay, look at here. What we have to do, Nana? I equals to, as usual, dq upon dt, but dq we have to write sigma dA by dt. Any mistake here, Nana? That dA I'm taking it as 2 pi x dx upon dt, where dx is nothing but what? Thickness of ring, means this thickness, shadowed, yeah, whatever I have marked with the black color, Nana. This one, shaded region. The shaded region is dx and its radius, radius of the ring, we are taking it as x. That x is variable, Nana, keep in mind. Okay, x is equals to radius of ring, assumed ring. Okay, so dx by dt, when it is rotated, how to find? Okay, so dx by dt, we can find out what, Nana? Are you able to follow my point? Dx by dt gives what? Is it velocity? Sure. Correct, Nana? Yes, yes, yes. So here I equals to what? Sigma into what we write? 2 pi x into dx by dt. That is V. Okay. But problem is V is variable with x, Nana. Why? Because omega we are taking it as constant. It is rotated with some constant angular velocity. Again, what we have to write? Sigma into 2 pi x. V is equals to x omega. Any mistake here? Right, good. Then I equals to, I'm going to write sigma into 2 pi omega into x square. So look at there. Here to find out the equivalent current developed when it is rotated with some constant angular velocity, different regions are getting different currents. You understood this point? Different regions of disk. Right. It is looking like concentric circles, forming concentric circles continuously with the changing of x, producing some current. Okay, just like the orbits are producing the current, in the same way here, this is producing the current. Okay, so we can't integrate it further, Nana. Is it possible to integrate it further? No. Yes, exactly. That's what I'm saying. Okay. That implies I is equals to, if you want to substitute sigma, why? Because sigma is not given to you, Q is given. Sigma is total charge divided by total area, that is pi r square. Total radius is r. Okay. Times, here look at there, that is 2 pi omega times x square. Means you are getting what, Nana? Q omega into x square upon r square. This is the equivalent current W. That is, it is looking like I is directly proportional to x square. That implies I is different for different values of x. This is the story now. Okay, all of it followed here, this kind of model. Okay, generally what they ask, sorry, you said it is previous advanced, means advanced type of question. Yes, what they ask, how the current changes with the radius, means a graph they require when you come to advance. Means I, this is the radius. Ah, very good, very good, very good. Where r is the distance from center, distance from center of disk. Parabola y equals to ax square model. Y equals to ax square means symmetric to y axis or x axis in the parabola. Means you will get a parabola like this or like this, symmetric to x axis or y axis. Ah, symmetric to y axis, exactly. Okay, not this one, symmetric to x axis, it is symmetric to y axis. We will get a parabola here like this. Don't put the another parabola here, Nana. Radius negative value is not possible. Okay, don't draw like in mathematics. This is wrong. Means you are saying that radius is negative. So we have only positive parabola. Okay, did you follow now, all of you? Yes, yes, yes. Any doubts in today's class? Right, good. So successfully today we have completed the applications of I equals to q by t. Okay, right, tomorrow we will start the class with another concept. Okay, Nana? So shall I stop the class here? Okay, Nana. Bye everyone, Mari.